Hello, everyone. Thank you for waiting, and thank you again for being here today for our live session, producing nanoaerosols by spark ablation using the VSP G1 Nanoparticle Generator. My name is Andrei Linka. I am content creator for VS Particle, and I will co-host today's session with my colleague and VS Particle CTO, Dr. Tobias Pfeiffer. Before we get into today's topic, I would like to walk you through today's agenda. We will discuss handling questions during the presentation, webinar recording, upcoming events. I will then give you a few ways in which you can get in contact with us and request additional information, a short introduction into VS Particle Company for people who are not yet familiarized with what we do, before we dive deep into Pfeiffer's presentation, producing nanoaerosols by spark ablation using the VSP G1 Nanoparticle Generator. The topic will be an introduction into several basic aerosol processes related to the generation and transport of nanoaerosols. The generation of aerosols by spark ablation is presented in the context of these processes, and several use cases in test emissions, nanoparticle exposure, and toxicity studies will be discussed. The last part of today's webinar will handle your questions. Please note that you are mute during this session, so you won't be able to speak. Any comments or questions you might have, post it in the chat box. We are taking questions during the webinar, and we will try to answer all of them after the presentation has ended. Although for the questions that remained unanswered at the end of the session, we will do a follow-up email in the coming days. Also note that it's very important for people who do not have a Teams account to attach their email to the question so that we can reach you afterwards. You can find the chat room in your bottom right corner, the question with the icon with the question mark. This webinar session will be recorded, and we will send you a link in the coming days so you can share it with your colleagues or watch it later. We have two more upcoming webinars: Enhancers, cutting-edge search substrates made with VS Particle technology for quick and clear molecular analysis. It will premiere on Thursday, December 10th, 2020 at our usual time. And Accelerating Gas Sensor Composition Screening with the VSP G1 Nanostructured Material, which will take place somewhere next year. Please follow our homepage and website so that you can register also for the enhancers and get information for when the gas sensor composition screening will premiere. We are happy to provide additional information, and there are many ways in which you can get in contact with us and request additional information. If you would like to know more about VS Particle solutions and how they can help you in speeding up your research, you can check our other application pages for more information at www.vsparticle.com/applications. If you are interested in trying out VS Particle technology, you can do so by requesting a demo and try it in the safety of your own labs. Please check the form for more details at www.vsparticle.com or by email at demo@vsparticle.com. And for any other information, please always get in contact with our sales department at the email sales@vsparticle.com. VS Particle is a spin-off company of TU Delft, located in the Netherlands. With over 20 years of experience in the synthesis of aerosols, and with the help of a young and passionate team of engineers and scientists, VS Particle is unlocking a whole new world of possibilities at the nanoscale. As we all start to understand these possibilities, it will enable research and industry to rethink production processes and develop new materials to create innovative applications. We develop and commercialize completely new technology to automate the production of new materials, and we are key nanotechnology providers in different industries like catalysis, semicon, and health. Since 2014, we have helped scientists and industry all over the world to drastically reduce the development time of new materials and products by enabling automated nanoparticle production. We also provide products enabling the production of nanostructured materials for fundamental and applied research based on a simple to operate and scalable principle. And here you can find a layout of our current product portfolio. Thank you everyone for bearing me through this short introduction. I would like now to give the floor to my colleague Tobias so he can dive into today's topic. And I will talk to you at the end of the session when we will take your questions and follow up with the answers. Thank you so much, and I will speak to you soon. Tobias, you have the floor.
Hi, Andrea. Thank you. So welcome everyone. Also on my behalf, my name is Tobias Pfeiffer. I'm going to talk a bit today about producing nanoaerosols by spark ablation using our VSP G1 Nanoparticle Generator. As Andrea mentioned, there are many applications for nanomaterials, and most of the people that we work with focus on the materials themselves, right? So this is something tangible, something you could make and you can build on. And these materials then start having a function in another process. What I want to talk about today more is about how you make these materials and the particles that constitute them. And specifically, I want to answer the question a bit, should we care about the particles just by themselves? This is for us an important question because well, we use the particles to make such materials. And I'd like to take along a bit about how we look at working with small particles. So I'll give a bit of a motivation about why I will talk about this, describe some aerosol basics, talk about how you could make nanoaerosols, then focus, of course, on the G1 a bit, and highlight a few applications where it's not so much the materials themselves, but the particles that we are interested in. So at the basics, what is an aerosol? An aerosol, well, the word itself is something with aero, so gas, and solution, so something that is dissolved or suspended in a gas. Typically, these are particles or droplets. And there are many, many names that we can have for those. Smoke, dust, haze, cloud, fume, fog. Doesn't really matter that much. They all have one thing in common, namely it's a denser phase in small discrete elements dispersed in a gas, and it's a ridiculously broad topic to deal with because the particles could be solid, they could be liquid, they could be biological. Perhaps the most important aerosol that we're thinking about now are virus particles that can be transported along. They're the same as a cloud, just slightly different. The particle size changes over many orders of magnitude. As long as it's below about 100 micrometer, these particles can stay afloat for a pretty long time. The mass concentration, because well, basically you get the cubic power cube of the particle size in there, that rapidly crosses even more orders of magnitude. Number concentrations can be very low, from a couple of particles per cubic meter in a clean room up to well, 10 to the 20 if you go right at the mouth of a volcano or at the top of a flame. Very standards to keep in mind with aerosols, that they have a very limited stability. Right? Most aerosols are, especially under a second old, they are continuously evolving, they're continuously changing, and slowly they will decay until they're a more stable thing over the course of years. But where you're practically working with them, they are always changing. Luckily for us, we can focus just on room temperature and room pressure. So at least some things are somewhat stable. And of course, I'm cheating a little bit there because especially in manufacturing processes, you sometimes go to higher temperatures and sometimes you want to work at higher or lower pressures as well. But still, there's ways of handling these materials. First of all, of course, aerosols are everywhere. I'm sure most of us are aware of that, especially, well, the most common aerosol generator that you run across is a person, because whenever we're talking, whenever we're singing, whenever we're laughing, we are ejecting small particles and they are traveling through the gas. And well, a lot of them end up in the floor because they're heavy, and smaller ones may travel along. And if you're not very careful, then before you know it, you have a global pandemic, and we're having these events from the comfort of our home instead of face to face. These particles also travel differently because of different sizes, right? So it's not just when you're generating them, when you're transporting them, but also inside the human body when you're breathing the air. Particles end up at different locations. So what you will see in the graphs to the right, the top shows in blue where particles are collected. When you breathe them, if they're sort of what particles are collected inside basically the head. And you see that the bigger particles around 10 micron and the very, very small particles, they get captured rather efficiently over there. Keep in mind that the vertical axis is 1%, so it's not complete perfect filtering here. And as you go deeper down into the lungs, you get smaller and smaller particles captured. And that offers up interesting opportunities. For example, if you see this little peak at about 10 nanometers here, you could, for example, consider delivering a drug very selectively into the alveoli of a human person. Or you could have a malign particle floating in the air very effectively deposit in there. So it's important that we understand how these aerosols work. And for those that are not familiar with them, I will dive a bit into some basics on that. So the first thing to keep in mind is when we're talking about particles, most particles, at least when they're solid, they are not nice spheres. They tend to be chunky, they might be a bit crystalline, they might have very open porous structures. But for practical purposes, we of course simplify these to spheres. And then you get different choices to make, right? Do you model it as a sphere of the same physical size? When you look at the particle, well, that's for most applications not that useful. So instead there's a couple of diameters that are very common in aerosols, aerosol science. One is the aerodynamic diameter, which is basically how a particle reacts as it travels through a gas, sort of slowed down by the molecules traveling around it. And the other is the mobility diameter, which is slightly different, which tends to be, at least at smaller particle sizes, more correlated to diffusion. Because there's two main modes of transport that I like to mention here. There's convective transport, so big particles, they tend to travel along with where the gas goes. And the small particles, they are affected strongly by Brownian motion and they will travel all over the place. And that has impact with how we try to collect particles and how we handle particles in general. We see on the left here is a fiber, a single fiber in a filter, and there's gas streamlines traveling around it. And what you'll see is that both small particles and big particles can be captured effectively, but by very different methods. So if you take a typical HEPA filter, for example, or let's say a face mask, the fabric that's in there, any aerosol that goes through it, very small particles will travel through these small holes in the fabric, but they will still get captured because they will move around. And the bigger particles, they don't follow streamlines either. They can go straight and impact directly on the fiber. And all that combines into this graph here to the right. Basically, these graphs are, by the way, from Aerosol Technology by William Hines. If you want to know a bit about aerosol science, want to get started with that, I highly recommend that book. It's very clearly written and it quickly gets you the basics that you need to know to handle with 90% of the cases. So anyway, in this graph is shown for a filter consisting of many, many fibers, the collection efficiency. So 100% is all particles are captured, and what you see from here is that sort of below 200 nanometers, diffusion is the dominant mechanism. You can mostly ignore other mechanisms, and above about 300 nanometers, impaction and settling are the important ones. And because we tend to care mostly for particles about 20 nanometers, diffusion is the dominant effect to worry about. And it is also what you will very effectively see if you try to work with anything below 20 nanometers, you will lose your particles to anything. The walls of your system that you're building, for the tube walls or any obstructions that have you in there, quickly collect all particles. And so we need to figure out a way of reducing that available surface area. The second important aerosol process I want to talk about is Smolakowski growth or coagulation. And this is the effect where you have particles floating around in a gas. There's nothing keeping them apart. So once they collide, there's a non-zero chance that they will stick together. And when they stick together, they form a bigger particle. And in this case, I'm showing some droplets here. So you have two small droplets combining together to form a bigger droplet. And of course, those bigger droplets can then continue growing until they form an even bigger droplet. What's interesting is that equation behind it basically is the NDT, so the concentration, the derivative of the concentration versus time. Beta is a coagulation kernel, which takes into account the size of the particles, but below about 20 nanometers is roughly constant. And again, the concentration. So effectively what we have is an equation which only has the number of particles that we have and time in there. And that gives us the two tools that we have, the two knobs that we have to dial our particle growth process. We either have to be fast or slow, or we need to have more or fewer particles if we want to control our particle size. And of course, the particle size in this case scales only with the third power, because we're looking at the diameter versus volume here. Now, if we're talking about solid particles, something funny happens. That is, at a certain point, you no longer get these nice spheres occurring because the particles are not molten. And so you can get weird shapes, and that keeps going until you start getting fractal agglomerates. There will be a TM image a bit later on that describes it in better detail. But that shows also how you can quickly get particles that very much are not spherical, that can have relatively small primary particle sizes, so these individual units, but together as a bigger particle, they behave as a somewhat bigger particle. Now back to this equation for the particle growth. This very nicely reduces to this simple graph, where you have on the y-axis the number concentration, and on the x-axis the time. Both are logarithmic. And what you see is the maximum concentration an aerosol could have in theory after a given time. And so if you wait long enough, let's say a day, then an aerosol will not have a concentration over about 10 to the 5, 10 to the 4 particles per cubic centimeter. Now, in our case, when we try to work with making materials or trying to do experiments, we of course want to have a lot of particles. And so that means we have to work at very short timescales. Typically around a second, or preferably well below a second if you want to have large numbers of particles. That's something just to keep in mind with what we're doing. And at this point, I want to switch more to about how you could make particles for aerosol studies. So how do we make nanoaerosols? Well, the first method is atomization, and there's many variants of that. It's a top-to-bottom approach. You take a liquid and you can disperse it through a jet or a nozzle or anything like a sharp edge. And this liquid is shot over that at a high pressure and is quickly dispersed into tiny, tiny droplets. They tend to be about a few microns in size. And if you want to make smaller particles, you could, of course, do that by dissolving something or suspending something inside this liquid. So if you take a suspension with nanoparticles of a few nanometers and you make sure that's just 1 nanoparticle per droplet, you can get very nicely very, very small particles from there. Or you could dissolve a salt or some other compound into these droplets, and when you evaporate the liquid, you end up with smaller particles as well. Of course, the challenge with that is you will always have some solvent remaining, or there might be some precursors left. So depending on the purity requirements of your process, of your test, this may not work. And there's many, many ways you could do variants of this, right? So spraying of all sorts, they are very common. Electrospray is very interesting, where you use an electric field to draw the particles even smaller. That's a way of getting very, very small droplets. And vibrating orifice and hundreds more, I'm sure. Another important process, one that we see around us mostly every day, is combustion. This is more bottom to top, right? So we take a fuel and we burn it, and then there's two routes. You either have not all of the fuel being combusted, and that leaves you with some soot type material, carbon, and then some other stuff that will form particles. Or you could add some precursors to the fuel, for example, a metal salt, and when you burn everything away, you have a metal or a metal oxide remaining after that. What's challenging with these is that your gas composition changes, right? So you start with something that contains carbon dioxide, some water's in there, there's typically some nitrogen still in there. You might not have combusted all your fuel. So without even looking at the particles, already a pretty complex system. And then you have to deal with what the particles did. But having said that, it is a very common method of making particles, right? Engines are typically used. You could use a flame, or flame spray pyrolysis is a common way of making very nice particles for materials production. One issue with these materials is they're difficult I think, for making test aerosols, right? An engine tends to be bulky, a flame is finicky and tricky because you really have to manage your fuel and your airlines well. And any change in humidity or temperature will give you completely different results. And the other method is also not very suitable for more inline type production. And a third method I would like to talk about is evaporation and condensation, which is basically a physical approach. Again, bottom to top, you take a solid or a liquid, you evaporate it, and you've got a nice vapor of molecules or atoms. And when you start cooling that down, that starts condensing to form small particles, basically along a similar process or the same process that I described before about the coagulation. Right, so it's predictable. You just need the number, concentration, and the time. And you can control your particle size very effectively. As long as you know what your quench rate is. Your quench rate will determine a couple of things, namely how quickly the particles start coalescing and coagulating, but also for your primary particle size. If you have a slow quench rate and your aerosol stays warm for a long time, you'll end up having bigger primary particles, and that is something we're trying to avoid. What I like about evaporation condensation methods is they can be really simple. You have nitrogen coming in, you have a material that you're heating up, and you have just nitrogen and that material that you've heated up coming out. So it's very pure in theory. And there's several variants of that. Tube furnaces are used a lot, which have the drawback that it's a large volume that you're heating up with potential contaminants coming from there. A glowing wire is very nice in certain niche applications, but has some practical challenges where the wire sometimes breaks. Arcs are good if you want to have a lot of mass, and of course our preference is the spark, which is a controlled discharge that gives you a nice balance between output and very small particle sizes. And to go more into detail about the spark ablation, then effectively what we do is we take 2 bits of metal or any semiconductors. It needs to be reasonably conductive. We flow an inert gas through that. And we apply electric voltage. Basically, there's a capacitor with a high voltage over it, and that will then discharge, and you get a spark, and that evaporates the material just from the surface. And so we're just heating up these tiny little bits of surface at these electrodes, so you can get very pure with that. And this vapor then starts coagulating, starts growing, you start getting atomic clusters of a few atoms in size. Then we call primary particles or singlet particles sometimes, which tend to be, let's say, about 3 to 4 to 5 nanometers. Some materials a bit bigger, some materials a bit smaller, until eventually you get to aggregates and agglomerates, and they look something like the graph to the right, which is actually a mixture of 2 types of particles, aluminum oxide and gold mixed together, which ends up being this open, fluffy structure. And what's nice is you can control this quite effectively because you're just dealing with the flow of gas and the energy into the spark. And I'll get back to that later. Now, our nanoparticle generator, the VSP G1, is convenient for many lab applications, specifically because it's a desktop system. It has a decent output, depending on the material, you can reach about 20 milligrams an hour or more. And you could start from a single atom. We've seen that with APIT, also atomic flight mass spectrometry. That you can go single atoms, silver 1, silver 2, silver 3 coming out. There will always be a distribution. You don't get the single particle size directly from the generator. And of course, you can imagine if you start working with single atoms that you're going to have a different production rate than if you're going for bigger particles. So don't expect 20 milligrams an hour of single atoms coming out in a useful way because they will quickly start coagulating. And of course, what's good to know is that these are available worldwide. They are worldwide in Europe, in Asia, the USA, and Canada. And if I didn't include your country in the list, my apologies, but of course, we can also get it there. So what comes in? There are some semiconductive electrodes you could easily mount in there. You just open up the reactor, click them in, and you're ready to go. We tend to work with inert gases. Some people add traces of oxygen, for example, to create oxides. but it's convenient just to start with an inert gas. The voltage on average is about 1.3 kilovolts. The actual discharge occurs at a slightly higher voltage. It runs at a current of up to about 10 milliamps, so in total you get about 13 watts effective power from the G1 here. And it works at room temperature, both on the outside and effectively on the inside. The gas will warm up a bit, but everything is basically, you can touch it when it's running at full power and not burn yourself. So it's a cool technique in that sense. What comes out is an aerosol of pure ligand and solvent-free nanoparticles. The primary particle sizes are basically always below 20 nanometers. We tend to have aggregates, of course, if we start growing bigger particles or if you start giving these aerosols too much time to grow. And the ablation rate is element dependent, and I'll come back to that later. And so if you look inside this reactor, there's two interesting, there's an interesting feature with our G1 is that you can configure it in different ways. So what you see here on the image is a TP. So there's a tube coming through here, there's a gaslet inside coming through, and inside here there's the gap where the two electrodes are placed against each other. A viewport here so you could look what's happening inside the spark. But you could also replace this T-piece with a 4 or 5-way cross, which allows you to have gas flowing from the front to the back or back to the front, so perpendicular to the screen in a crossflow configuration. And those give you different sort of outputs. So if you look here in the graph here, this is what we call a through flow configuration, because the gas flows from the left through the electrodes out to the right. A spark occurs between these electrodes, and the vapor is transported away through this very small volume compared to the rest of the system. Right, and as I said before, we just have concentration and time to deal with. If you have a very short residence time, you get small particles. If you have a very small power, then you have a low amount of material evaporated, so you also get smaller particles. Go the other way around, have a long residence time, having either bigger volume or a lower flow rate that gets you bigger particles, and having more power will also give you bigger particles. That's why this crossflow configuration is interesting, because for people that want to have bigger particles, then it's more convenient to just use this big diameter from this KF system. So it's about 40 millimeters internal diameter. So you already have some immediate agglomeration inside the chamber here. And you can continue with high flow rates and relatively high concentrations of bigger particles effectively. So there's a way of using the same system either for the very, very tiny stuff or the somewhat bigger stuff. As I said before, what comes out are particle size distributions. By themselves, they're not monodisperse, but for example, you have something like this. This is measured with a differential mobility analyzer, a DMA, where we look at the, let's say, the projected size, kind of like a kite. How bigger the particle is, the bigger the resistance it will experience as it's being pulled through a gas. And we use charged particles here. There's always a small fraction of the particles that have a charge. And so if you have a positive charge, you can use an electric field to drag a particle through this field and use that to separate out a particle, kind of like a mass spectrometer, but then at atmospheric pressure. And what you see is that we get primary particle sizes, mobility sizes of around 4 nanometers, and with TEM you'll see about the same thing, 4 to 5 nanometers in particle size, with a bit of a tail going to bigger particles. Those will be agglomerates, but also some smaller particles. All in all, it's pretty narrow distribution for many applications, and there are ways of making these even more narrow using that same DMA. But that's a topic for another presentation. What is interesting, if you start looking at this graph, this is just at one set of settings. What we do is we expand this to a whole bunch of measurements. And so we get these sort of heat maps, and what you see here is the position of the mode given on this axis here. So we're talking from 2 nanometers up to about 80 nanometers in size. The mode shifting with spark power on the y-axis and the flow rate on the x-axis. So what we see here is if you take, for example, a flow here, that if you start increasing your power, you will slowly go to bigger and bigger and bigger particle sizes. And the same way that if you start reducing your flow rate, you also go to bigger and bigger particle sizes. So if you want to have the smallest particles, you tend to go to a low power and a high flow rate. In this case, in the case of gold, you'll see it's actually the smallest particle sizes you could get even at higher powers. And that probably has something to do with either losses, that we lose too many particles at the low powers, or a measurement inefficiency in our DMA system. So I wouldn't be too confident whether this is actually a significant difference between the low power and the high power here. And in fact, what you see is with these graphs is a similar trend all over the place. And these are all in, I'm pretty sure that these are in argon. If not, I will correct that afterwards, in the email. This is for gold, for platinum, and for zinc. You'll see similar sort of behavior. And we have this for a bunch of elements. And if we don't have a specific element, we can typically make one of these quite quickly to just get you started figuring out how to configure your G1 to start getting the particle size that you need. The main take home here is flow rate is an important way of controlling your particle size. If you're going to work with milliliters per minute, don't expect the tiny particles. And typically you can control the sort of mode of the particle size quite easily here. And this is just at the outlet of the G1, right? So if you start adding a volume downstream of that, you can grow these particles even bigger. So there's a bit of a material dependence, but the general trend is consistent throughout these things. So moving on from there, applications of nano-aerosol generators. I'm going to highlight a few case studies of basically aerosol science, or basically people using spark generators to study properties of small particles in the gas, mainly related to how they interact with people. The first one is emissions testing. So this is where we're trying to figure out how we could have workable standards for the quality of air related to, well, basically cars, right? That's the whole topic. Cars are running out combusting fossil fuels and they're emitting all sorts of nasty stuff out there, and we have to regulate that. But we need to make sure that these are sensible regulations that both protect economic and health interests. And so what we have are emission limits on the vehicle exhaust related to solid particle number. So how many solid particles are in the gas? But these are regulated for 23 nanometers and above. And there is a significant fraction of the particles in about the 10 to 23 nanometer range. And there are indications that those smaller particles are actually very harmful, for example, in terms of brain diseases. And heart disease. So this is something that is worth looking into, but there's still a practical issue with it's difficult to detect these small particles, and because we don't have good detectors, we cannot really regulate it down to these small sizes. So there's a lot of work going on that side. On that side, both trying to develop these calibration methods, but if you want to make these calibration methods or these measurement methods, you also need to have a particle source that can make these 10 nanometer particles. So this chicken egg problem we're trying to sort of help out with. So this is research performed at the Joint Research Center of the EU in Ispra, Italy. And there they looked at trying to see what they get from 10 nanometer CPC. So the particle counters that they're using tend to have a cutoff around 23 nanometers. And there are CPCs out there which go to smaller and smaller sizes, but those are not validated yet for such standards. And so what they did in this work is they used the G1 to make some reference aerosols. They shifted the mode from about 17 to about 64 nanometers. And what you see is it's a distribution with which they can span a large range of particles. They also studied the charging of these particles. And it's shown in this graph at the bottom here. So the black line is the frequency or the abundance of single charged particles versus, in this case, double charged particles. So we're not looking at the neutral particles, just want to know if there are double charged particles or not. If you look back at this DMA, this size selection thing, having multiple charges makes it a bit more annoying to correct for what the actual particle size is. And what you see is such a setup typically looks like you have a particle generator. You may want to dilute the flow coming out of this. If you have too many particles coming in, you go through a differential mobility analyzer. In this case, they use the neutralizer. We don't recommend it. We don't disrecommend it. In our experience, we get slightly lower charge distributions, slightly lower charge concentrations with the G1 compared to a neutralizer. But as soon as you go through a neutralizer, diffusion losses outweigh any benefit you have from the neutralizer. So then it tends to be easier to just not use the neutralizer. You typically need to go through a second diluter because you have sensitive measurement equipment down the line. In this case, they had a couple of particle counters for 23 and 10 nanometer cutoffs, a reference counter, and a Faraday cup, so an electrometer that measures the charge coming through. So this is a way that you could use these machines. Basically, their conclusion boiled down to you could use such small particles, but there's of course some more work needed. Moving on, nanotoxicologies. The second application I wanted to highlight, and this has to do with once we get these particles emitted in the air, for example, from a engine, but also from man-made products. We could have all sorts of particles in there. They could be inhaled and they will end up somewhere in the body, perhaps. And so a valid question to ask then is, where do they end up? And does particle size have any effect once they end up in the body? So this is a study performed by a group in Edinburgh, UK, and a couple of groups in the Netherlands, where they did a study on healthy volunteers to try to see where these particles end up. And you see again where in this graph, the mobility size of these particles tends to be, let's say, 20 to 30 nanometers in size. They're pretty big and they will transport quite deep into the lungs. But the primary particle size is in this case about 4 nanometers. So they are built with very, very small particles, have a very large surface area. And if those small particles can let loose or start dissolving, they might transport in a very different way. Now, what they concluded is size matters. If you have a small particle, that will behave very differently from a big particle at the same dose. And what's more interesting is that you could see that these particles will translocate, so they travel through the body. They don't just stay in the lungs, but they end up in different places. In this case, they even saw particles, gold particles, ending up at the site where the disease was. So they cut the bad parts out of a person, and they found in there these particles. So that might mean that this is a route, or that means that this could be a route by which small particles do influence our health. Of course, this is more work is needed on this, but also good to know in this case that they still found this gold in blood and urine for over 3 months. So once you inhale these particles, they're not that easy to get rid of. And finally, I want to talk a bit about a project that started last year. It's called TUBE. It's transport-derived ultrafines and brain effects. It's Horizon 2020 research in action with about 16 partners all across Europe. And in that, we try to study the adverse effects that ultrafine particles could have on the human lung and brain. What I like about this project, it's very multidisciplinary. It goes from the basics, so trying to see how the particles are formed from traffic engines and simulated emissions. So there's measurements both out on the street, there's engines in a lab, and there's test systems like a spark generator, and try to see if we can connect those devices so we can have reliable measurements no matter where we are. There's a bunch of characterization going on as well, because once you have this aerosol in the gas phase, you want to sort of figure out what it looks like. People are looking at how to deposit these things to some extent in vivo, but mainly trying to get also everything done in vitro, because even though you might sometimes need to study in people and animals, it's of course much preferred if you could just do that in a device. My apologies. And of course, where the particles end up, so translocation, And finally, also including the toxicology and if there's any biomarkers occurring, which we could use to figure out what's going on in there. I'll happily keep you updated more about this at a future date when more information comes out. But so far, some things I could talk about is when you need a whole bunch of infrastructure to do these measurements, right? And it gets very challenging because we're trying to compare real-world situations versus the lab, and they are very different. A whole bunch of the techniques are online. A lot of aerosol instrumentation gives you immediate results, but a lot of the biological assays, they tend to take more time. So these are offline. How do you compare those things, especially having an unstable aerosol? And of course, the chemistry is rather complex as well. Our goal in that is try to figure out if a spark generator could be a good reference source for ultrafines, because, well, engines they're just bulky. You just need a lot of space to get them running right. Flames, they are not very convenient sometimes because they have a mind of their own. And in theory, at least, the spark should solve these problems, and that's something that we at least are hoping to prove as part of this project. So to conclude, the main take home here is airborne transport is important if you want to know where ultrafine particles end up. Aerosol processes are dynamic in their nature, so you need to take your whole system into account. It's not just, hey, I make an aerosol with a certain particle size and concentration and I'm done. No, because you still need to get that aerosol to where it needs to go. And finally, I've shown that the G1 can give a rather dynamic range in particle sizes, but also in output for both carbon particles, but also a lot of other test aerosols, metals and metal oxides. If you want to know more about the metals and metal oxide stuff, then it's interesting to talk more about the material side of things, but that's what our other webinars are for. And so with that, I will give the floor back to Andrea. I'm sure that there's a lot of questions. I've seen some things pop up. So let's move on to the Q&A, Andrea.
Thank you so much, Tobias. I hope everyone found this presentation insightful and interesting. We do have quite some questions. So I will proceed to reading them and we will get our answers from Tobias. First question is, for calibration purposes, what are the concentrations that we can achieve around 10 nanometers with your system? Tobias?
Yeah, so 10 nanometers is a bit tricky sometimes, typically about 1,000 particles per C. If you optimize things, maybe 3,000 or 4,000. And this is very dependent on the flow rates that you're willing to have with that. So if you can deal with a high flow rate, you could bump it up a bit. But that's the order of magnitude that you're looking at, several thousands.
Thank you so much. Going on to the second question. What would be the electrical charge of the generated particle, positive or negative?
Both. Particles, it's a bit dependent on gas composition, a whole bunch of other things, but effectively what you should do is look into what a neutralizer does. So you have the Boltzmann distribution, and the particles coming from the spark are usually pretty similar to that. Only if you work in extreme gas types, you would get a different thing, but you would get a different thing with the neutralizer as well. It tends to be slightly lower in concentration, let's say 5 to 10% lower than you get with a neutralizer. But in our experience, when you go to then the smaller particles, the diffusion losses outweigh this effect.
Thank you. Somebody is asking us, do I need to use a neutralizer to charge the particle produced by the G1?
Basically what I just said, it's not necessary. There might be an advantage in terms of reproducibility. We've never really studied that. My gut feeling is that, basically in my experience, you get very consistent results similar to a neutralizer. So unless you are trying to have a completely validated process out of the box, I think you're always going to be better off without the neutralizer. Controlling your gas composition is more important, even with the neutralizer.
Thank you. Would it be preferable to use electrodes like shown in the previous image, cylinders empty inside so the gas with particles can flow through them, rather than using ones who look or are like wires? Somebody's asking.
That depends a bit. So what I try to highlight is that these hollow tubes have as an advantage that your gas exhaust is this tiny little tube coming out instead of this bigger reactor volume, right? So it's a massive change in volume. You go from 100 of cc's down to a couple of cc's, and so your flow with the same flow rate, you have a much faster displacement to get these particles out. And so if you want to get the tiniest particles, let's say a few atoms in size, go in a through flow configuration because you can get the spark so much closer to your measurement device. And for the rest, yeah, a wire versus a thick rod. So we tend to not use wires. We use slightly thicker rods because they just last longer. With a thin wire, you typically get a slightly higher output compared to a thicker electrode, and that has to do with heat being transported away.
Thank you. Hope that answered the questions. As the electrode material gets used up, the distance between the electrodes would change. What effect would that have on the output?
So what happens in the G1 is one of the electrodes is fixed and the other is moving, right? And so as we are slowly ablating away these electrodes, they tend to be like about 25 millimeters of usable space. So you could eat away from both sides about 50 millimeters. That's quite sizable. So we have to keep closing this gap. And so what happens in the through flow, it doesn't have too much of a difference because you just shift your gap a little bit. In cross flow, it does matter a bit. And at some point, it's worthwhile to start swapping electrodes if one side becomes much shorter than the other, because you'll see that the gap where the spark occurs slightly moves from the center of the reactor. But this takes weeks, right?
Thank you, Tobias. I think we will be moving on to the last question of today's session as our time is getting up. Martin Irvin asks, do you have issues with particle concentrations being too high for CPC single count mode, or does using a DMA negate this? When using all those different flow rates to control diameter, are there issues with concentration high and low?
We quite often have way too many particles for a CPC. The DMA usually helps with that, but we can still flood a CPC under the right conditions. In terms of the flow rates, yeah, so we tend to work with a bypass, right? So if you want to have smaller particles, you just push more gas through and you sample at the end of this bypass line. There's some tricks with that. In principle, that is possible. And I hope that answers the question. Yeah, okay. Yeah, so basically, in terms of flow rate and concentration, a higher flow rate on the one hand means dilution, but you also have fewer diffusion losses. So typically, a higher flow will actually give you a higher concentration compared to a lower. Also because the residence time is reduced, right? So if you want to have a higher concentration, just use more gas. Counterproductive, counterintuitive.
Thank you, Tobias. I know I said that will be our last questions, but I overlooked one, so this will be the last questions. I have a question. How to ensure the accurate quality of nanoparticles when you do a toxicological experiment? Sorry.
That's a good question. How do you ensure that? It's difficult to say, right? At least what we can ensure is that what comes in is just the nitrogen and typically we're talking about nitrogen, then nitrogen and whatever element we have in there. So if we start with clean electrodes, you would expect to have clean particles as well, and you will typically also see clean particles. You would also have to make sure that the gas itself is clean. So if there's any organic compounds in there, you will tear those apart in the spark and you end up with some sort of soot formation on there. But if you compare it with other methods of making these particles, right? If you start from any liquid-based route, you also have a surfactant to deal with. That's not easy to remove. But I think in all those cases, you end up having particles that are something of a model, but they could never be a generic sort of perfect sort of thing, because you need to keep in mind the method by which these particles were made. But I mean, if you have a 5 nanometer gold particle with a ligand shell around it, then you actually have a 5 nanometer particle with a ligand shell as your particle, and not a 5 nanometer gold particle. And of course, once you have these particles, you can always collect them and start analyzing them with various techniques to sort of validate that you're studying what you are studying. But beyond that, I'm not sure you could. I'd love to talk more about that with the person in question, to figure out how to actually do that proper.
Yes, if you will please provide us with your email address, because you appear anonymous here, so we can do a follow-up email where we can explain more. And with that, I think we can wrap up today's session. Thank you so much, Tobias, for this presentation. We will keep in touch with everyone who attended, and we will send the recording in the coming days. And also we will answer the questions that remain here unanswered. We will leave, as usual, the event open for 5 more minutes so that everyone can address their questions if they didn't do so by this time. Thank you so much from my side. I hope I'll get to see you again in our future online endeavors. Next event is on Thursday, the 10th, the CERS application webinar. Please go to our homepage to register if you are interested in this topic. And I hope everyone had a good time, and I'll see you again next time. Thank you. Bye-bye.